Hello everyone. In this module, let me continue the wording problems of deciding the nature of a relation. Now, let us look at the question. Let R is a relation defined on a set of real numbers as A related to B. In the sense, a relation is defined, a relation between two elements A and B is defined if flooring of A is equal to flooring of B. Then determine the nature of relation R. Now, before getting to the problem, let me explain the basics of flooring function. So in mathematics, this symbol is used for a flooring function. So the minute when I write any value between these symbol, it denotes a flooring value. In the sense, I'll give you a simple example. Suppose if flooring of 4.3. Flooring in the sense, as the name itself suggests, it will take the nearest integer to 4.3. But that should be the least integer value. In the sense, the flooring value of 4.3 will be equal to 4. Similarly, the flooring value of 5.6 will be equal to 5. Similarly, the flooring value of 4.21 is equal to 4. Hope it is clear for you. Now, the relation is defined only when the relation between two elements is defined only when flooring value of A will be equal to flooring value of B. Then we have to determine the nature of a relation R. Now, first let us look at the nature of relation, that is reflexive. So as per the definition, so in order to prove reflexive, we have to take one element, only one element, right? So let me take the value of, or else let me take an element A. Fine. So if A is an element, we have to prove flooring of A will be equal to flooring of A. If this condition satisfied, then we can say R is reflexive. I'll give you a simple counter example. Suppose if I'm going to take A as, say, 2.3. Then again, to prove reflexive, I have to take the same element. So A is equal to 2.3. Again A is equal to 2.3. Then A is related to A. In the question, look at the question. A is related to B when flooring of A is equal to flooring of B. Similarly, since I am talking about reflexivity, so A is related to A when flooring of A is equal to flooring of A. Now, what is the flooring of 2.3? Is 2. So 2 is equal to 2. In the sense, for an element A, flooring of A is equal to flooring of A. That is, A is related to A. Therefore, clearly it is reflexive. Fine. Now, talk about symmetric. So as I already said, in order to prove symmetric, we have to take two elements. Let me take two elements, A and B. And I have taken A related to B. I have already taken this. So, as per the given problem, flooring of A will be equal to flooring of B. Now, I have to prove B should be related to A. This is what the definition of symmetric is. If A is related to B, then B should relate to A. Then only it will become symmetric. Now, if B is related to A, the meaning is that flooring of B will be equal to flooring of A. Now let me check, is it true or not? I'll give you a counter example. Suppose if A is equal to 2.3, the same value I'm going to take. Now let me take the value of B as, say, 2.4. Clearly A is different from B, right? A and B are different. I have chosen two different elements. Now first let me check about the first condition. Is A related to B? In the sense, first I have to check is flooring of A is equal to flooring of B. Now flooring of 2.3 is equal to value of B is flooring of 2.4. Now as per the definition of flooring function, 2.3 flooring is 2. Again 2.4 flooring is also 2. So A is related to B, it is true. Now we have to check the reverse of that. Is flooring of B is equal to flooring of A? Obviously it is true, right? Have a look at here. So B is 2.4, A is 2.3. clearly flooring of B is equal to flooring of A. So these two conditions satisfies. So I can say R is symmetric. Fine. Now transitive. Before going to transitive, first let me explain antisymmetric. Antisymmetric. So as per the definition, if A related to B, B related to A, then A should be equal to B. Then only we say it is antisymmetric. Right? Now let me take one counter example to prove this. So clearly take this example only, then only you will understand. Since A is equal to 2.3, B is equal to 2.4. Here flooring of A is equal to flooring of B, in the sense A is related to B. Again flooring of B is equal to flooring of A, meaning is B is related to A. Since A related to B and B related to A, but make a note that A is not equal to B. A is not equal to B. Therefore, I'll write once again, since A related to B, therefore flooring of A is equal to flooring of B. Again B is related to A implies flooring of B is equal to flooring of A. Now clearly A is not equal to B. Therefore it is not antisymmetric. Therefore it is not antisymmetric. Clear? Now fourth one is transitive. Transitive. So as per the definition of transitive, let me take A related to B, in the sense flooring of A is equal to flooring of B, and B related to A implies flooring of B is equal to flooring of A. I have to prove B related to C, right? Let me make this as C. I have to prove A related to C, in the sense I have to prove magnitude of A is equal to magnitude of C. I'll prove this by counter example. Let me take the same value, A as 2.3, B as 2.4. Since I'm proving transitivity, so I have to take 3 elements. Let me choose the value of C as say 2.2. Fine. Now let me check the first condition. Is A related to B, in the sense flooring of A is equal to flooring of B? Yes, it is. I have already done this. Flooring of A is also 2, flooring of B is also 2. So this condition satisfies. Again, now let me check. Is flooring of B is equal to flooring of C? What is the value of B? Is 2.4. What is the value of C? Is 2.2. Now clearly flooring of B is equal to flooring of C, because flooring of 2.4 is also 2, 2.2 is also 2. So this condition also satisfies. Now let me verify, is flooring of A is equal to flooring of C. What is the value of flooring of A? Is 2. I have already done this. Flooring of C is 2. Clearly this condition also satisfies. So therefore it is transitive. Since it is reflexive, symmetric, transitive, therefore we can say it is equivalence relation. It is not an antisymmetric, so we cannot talk about poset or partially ordered set. Hope it is clear. Next concept is composition of relation. Composition of relation. So before getting into the topic of composition of relation as per your syllabus, let me revise the basics that you have already studied in your second PU. Composition of relations are, I'll give you a simple example so that you can quickly revise that, like GOF, FOG. These functions are example for composition of relation. I'll give you one example. Suppose if I have a relation R with an elements 1, 1, 1, 2, 2, 3, say 3, 4. And let me consider a second relation S with elements 3, 1. So when I said relation, remember it is the ordered pair 4, 4, 1, 4. Right? Now, composition of a relation in the sense, suppose if R is a relation from set R to S, if R is a relation from set R to S, then composition is represented by ROS. ROS. In your class 12, it will be something like F, G. So composition will be F of G. or G of F. Fine. Now, without representing the arrow diagram, since you are in higher level studies, so we can directly write R composition S. Look at here, first element is 1, 1. In the sense, 1 is related to 1. Now, check for the element which start with 1 in set S. Is this element, see here. End element should be same. In the sense, in R, I am going to choose 1, 1. In S, I have to choose 1, 4. Why? Because continuation of this element should be there. Then, in ROS, the element 1, 4 will be there. Fine. I'll give you one more example. See here. I have an element 1, 2 in R. 1, 2 in R. Now, look at the element in S which starts with 2. Which start with 2. Why? Because I have an end element 2 in R. So, I have to look at S. S is 2, 4. Then, this element will be there in R composition S. Is 1, 4. Again, I have written. Already I have written that. So, no need to write it again. Now, 2, 3. 2, 3 element is there in R. Now, look at the element which start with 3 in S. Is 3, 1. Therefore, the element 2, 1 should be there in its composition. Hope it is clear. Now, next look for the next element. Element 3, 4 is there. In R, element 3, 4 is there. Now, have a look on the element in S which start with 4 is 4, 4. Since continuation is there, so element 3, 4 should be there in ROS. Clear? This is what R composition S. Similarly, you can find S composition R. And is given by, now you have to check S elements first. In previous what I did is I have taken R elements first. Look at here. Now I have to take S elements first. See here in S, first you have 3, 1. Now check for the relation R in which it starts with 1. There are two possibilities. Either it is 1, 1 or it is 1, 2. See here I have taken 3, 1. When you are going to take 3, 1, continuation element in R is either 1, 1 or 1, 2. So if it is 1, 1, 3, 1 will be there in SOR composition, as I already told in ROS composition. Now, if this is the case, 3, 2 should be there in ROS. Fine. Now, take the next element in S. Since we are dealing with SOR, so first you have to take S element. Here it is. Second element in S is 2, 4. Now, do we have an element in R? Do we have an element in R which starts with 4? In R, we don't have. So, we cannot obtain any element in SOR for second element. Fine. Similarly, take the third element in S. It is 4, 4. Do we have any element in R which start with 4? We don't have. So, we cannot have any element in its composition for the third element in S. Now, take the last element in S. Is 1, 4. Now, check the relation R in which the starting element is 4. Do we have? So, we don't have. The only element in SOR is 3, 1 and 3, 2. Now, hope it is clear for you. Right? Now, suppose if you are going to find R square in a relation, it will be of the form R composition R. Remember, if you want to find R square in a relation, it will be R composition R. Similarly, if you want to find S square for a given relation, it is S composition S. Now, for the same relation R, let me find R square. Why I am explaining all this is, I will make use the same concept in the theorem. So, when I am going to do R square, it is something like R composition R. Now, let me write R elements here once again. 1, 1, 1, 2, 2, 3, 3, 4. I'll write one more time so that there will be no confusion for you. right? Now elements of R square will be, first take one element in R, 1 comma 1. Now next see the second set, it is R only, anyhow you can take 1 comma 1 R, another possibility is 1 comma 2. Why? Because there should be continuation of element. Now 1 comma 1 should be there in R composition R. Now 1 comma 2 should be there in R composition. Yes, so 1 comma 1, 1 comma 2. Meaning is that, suppose if R has an element say xy and yz. Suppose if R has an element say xy and yz, then R composition R or R square should contain an element xz. Make a note of this, it is important concept. I'll give you one more example in order to convince this. See here, I am writing R square value. R square is none other than R composition R. I have taken first element already I have taken, so let me take second element in R is 1 comma 2. Again I am doing composition for the same set. So let me choose an element in R which continues an element 2, 3. So 1 comma 3 should be there in R composition R. Fine. Meaning is that, suppose if I have an element say xy in R and yz in R, same element continuation, then xz should be there in its composition or xz should be there in R square. Remember this keynote. Why? Because we are using the same. So whenever I have this concept xy, yz, then in R square xz element will be there. It is understood. So please keep it in your mind. So hope so it is clear about the composition of a relation. In the next session, let me continue the problems based on composition of relation and its theorem. Hope it is clear for you. Thank you.